Black holes, the most terrifying, mind-bending, reality-breaking objects in the universe. And yet, most people think they know what they're talking about when they mention them. Oh yeah, black holes. They suck everything up, right? Wrong. Dead wrong. The rabbit hole of black holes goes so deep that by the time we're done here, you're going to realize that everything you thought you knew about space, time, and reality itself was just scratching the surface. So buckle up, because we're about to dive into the 7 levels of black holes, from the baby food astronomy you learned in middle school, all the way down to the stuff that makes theoretical physicists question their life choices. Level 1. Pop Science Black Holes. This is where everyone starts. Black holes are space tornadoes that eat planets and stars, right? This is the level where you think Event Horizon was a documentary, and you're pretty sure that if you fell into one, you get stretched like taffy and then crushed into a tiny ball. At this level, black holes are basically just really scary space monsters. They're the boogeyman of the cosmos. You probably heard about them from some Discovery Channel special where they used dramatic music and computer graphics that look like they were made in 2003. Black holes, the ultimate cosmic destroyers. People at this level think all black holes are the same size, and they all just sit there waiting to destroy everything. They have no idea about event horizons, Hawking radiation, or space-time curvature. To them, gravity is just a force that pulls things, and black holes are just places where that force got really, really strong. The most sophisticated thing someone at this level might know is that not even light can escape, which they heard somewhere but couldn't explain if their life depended on it. They probably think NASA is constantly worried about black holes coming to eat Earth, not realizing that if our sun magically turned into a black hole right now, the Earth would keep orbiting exactly the same way. This is the level where you think Interstellar was scientifically accurate in every way, and you never questioned why the black hole in that movie looked like a big bright donut instead of, black. Level 2. Textbook black holes. So you've graduated from pop science and maybe took an astronomy class. Now you know some actual facts. You understand that black holes form when massive stars collapse, that they have something called an event horizon, and that there's a point called the singularity at the center where density becomes infinite. You've learned about the Schwarzschild radius, maybe even memorized the formula. You know that stellar mass black holes are different from supermassive black holes. You understand that Hawking radiation means black holes actually evaporate over time, which blew your mind when you first heard it because how can something that traps light actually emit anything? At this level, you've probably seen the rubber sheet analogy for space-time curvature about 1,000 times. You roll a ball bearing around a bowling ball on a stretched sheet and think, ah yes, this is how gravity works. You understand that what we call gravity isn't really a force pulling you down, but rather the curvature of space-time. You know the basic types: stellar black holes from collapsed stars, intermediate black holes that we're not entirely sure how they form, and supermassive black holes that somehow grew to billions of solar masses in the early universe. You've heard of Sagittarius A, the supermassive black hole at the center of our galaxy. You might even know some of the weirder implications, like time dilation near the event horizon. You understand that from the outside, it would take infinite time to watch something fall past the event horizon, but from the falling object's perspective, it happens in finite time. This is the level where you start using terms like tidal forces and spaghettification correctly. You know that smaller black holes actually have stronger tidal forces at their event horizons than larger ones, which seems backwards, but makes perfect sense once you do the math. But here's where level 2 gets interesting. You're starting to realize that black holes aren't just objects in space, they're literally holes in space-time itself. Level 3. Mathematical black holes. Welcome to the level where the poetry ends and the mathematics begins. You've now encountered the actual Einstein field equations that describe how matter and energy curve space-time. You understand that the Schwarzschild solution isn't just a description of black holes, it's the exact geometric structure of space-time around any spherically symmetric mass. You know about the Reasoner-Nordstrom solution for charged black holes and the Kerr solution for rotating ones. You've stared at the Kerr metric until your eyes bled, trying to understand how rotation drags space-time itself around with it. Frame dragging isn't just a cool sci-fi concept anymore. It's a precise mathematical prediction that we've actually measured. At this level, you understand that the event horizon isn't a physical surface. It's a mathematical boundary defined by the point where the escape velocity equals the speed of light. You know about different types of horizons: the event horizon, the photon sphere, the innermost stable circular orbit. You've encountered the ergosphere around rotating black holes, that region outside the event horizon where spacetime itself is dragged around so fast that nothing can remain stationary relative to distant observers. This is where you first glimpse the truly alien nature of black holes. They don't just bend spacetime, they drag time itself along with them. This is where you encounter the first really mind-bending mathematical results, like the fact that if you could somehow survive crossing the event horizon of a large black hole, the spacetime geometry would force you to reach the singularity in finite proper time no matter what you do. Not because something is pulling you there, but because toward the singularity literally becomes a direction in time rather than space. You've learned about coordinate singularities versus real singularities. The event horizon looks singular in Schwarzschild coordinates, but if you transform to different coordinates, you realize the singularity was just an artifact of your mathematical description. The real singularity at the center? That's mathematically unavoidable. But this level also introduces you to the deep problems. The mathematics tells you that matter collapses to infinite density at the singularity, but infinity isn't really a number. It's a sign that your theory is breaking down. Level 4. Thermodynamic black holes. This is where black holes stop being just gravitational objects and start being thermodynamic systems with temperature, entropy, and all the statistical mechanics to go with it. Stephen Hawking didn't just discover that black holes radiate, he discovered that they behave exactly like thermal objects with a well-defined temperature. The temperature of a black hole is inversely proportional to its mass, which means the bigger the black hole, the colder it is. A solar mass black hole has a temperature of about 60 nanokelvin, far colder than the cosmic microwave background. This means stellar mass black holes aren't actually evaporating in our current universe. They're absorbing more energy than they radiate away. But here's where it gets weird. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This completely violated everything physicists thought they knew about how information and entropy work. Why should the maximum entropy you can fit in a region of space depend on the area of its boundary rather than its volume? This leads to the holographic principle, the idea that all the information contained in a volume of space can be encoded on its two-dimensional boundary. Your three-dimensional reality might literally be a hologram projected from a two-dimensional surface. Black holes taught us this. At this level, you encounter the black hole information paradox in its full glory. Hawking radiation appears to be completely thermal, random, which means it carries no information about what fell into the black hole. But quantum mechanics says information can't be destroyed. So where does the information go when a black hole evaporates completely? This is where you start to understand that black holes aren't just predictions of general relativity. They're laboratories for testing the fundamental compatibility between gravity, quantum mechanics, and thermodynamics. And they're telling us that at least one of these theories is incomplete. Level 5. Quantum black holes. At this level, you're no longer just applying quantum mechanics to classical black holes. You're trying to understand what happens when quantum effects dominate the gravitational dynamics themselves. This is where the mathematics gets so complex that even theoretical physicists often resort to analogies and thought experiments. You encounter the firewall paradox, which emerged from trying to resolve the information paradox. The argument goes like this. If information really does escape in Hawking radiation, then to preserve quantum mechanics, there must be highly energetic correlations right at the event horizon. Correlations so strong they would create a firewall that incinerates anything trying to cross. But this contradicts the equivalence principle, which says that spacetime should look perfectly normal to someone crossing the event horizon of a large black hole. You can't have both information preservation and a smooth event horizon. Something has to give. This level introduces you to the ER equals EPR conjecture, the idea that quantum entanglement and wormholes are the same phenomenon. Einstein-Rosen bridges might be the geometric manifestation of quantum entanglement. Black holes connected by wormholes might be the spacetime representation of entangled quantum systems. You start to understand that the question, what's inside a black hole might be fundamentally wrong. In quantum gravity, the interior and exterior might not be independent regions, but rather different computational perspectives on the same quantum information. The mathematics at this level often involves tools from quantum field theory, string theory, and loop quantum gravity. You're no longer just studying black holes, you're using them as probes of the fundamental structure of spacetime itself. Level 6. Holographic black holes. Welcome to the level where black holes become windows into the deepest structure of reality itself. At this level, you understand that black holes aren't just objects that exist within spacetime. They might be the key to understanding how spacetime itself emerges from more fundamental quantum information. The holographic principle, discovered through studying black holes, suggests that our entire three-dimensional reality might be encoded on a two-dimensional boundary. But at level 6, you realize this isn't just an abstract mathematical curiosity. It's pointing toward a complete reformulation of physics itself. You encounter the gauge-gravity duality in its full power. The AD-S-CFT correspondence tells us that a theory of quantum gravity in higher dimensional space is mathematically equivalent to a quantum field theory without gravity in lower dimensions. The black holes in the higher dimensional theory correspond to thermal states in the lower dimensional theory. At this level, you understand that entanglement entropy in quantum field theory has a geometric interpretation. The entanglement between regions corresponds to geometric connections in the higher dimensional spacetime. Quantum information theory and spacetime geometry are unified. You encounter the idea of emergent spacetime, that the smooth geometric description of black holes and spacetime itself emerges from the entanglement structure of quantum degrees of freedom. Spacetime is not fundamental. It's a derived concept that only makes sense at macroscopic scales. This is where you learn about quantum error correction in holographic systems. The spacetime acts like a quantum error correcting code, where information is redundantly encoded. You can lose access to large regions without losing information about the quantum state. You start to see black holes not as exotic astrophysical objects, but as fundamental features of how quantum information and geometry are related. Every quantum system with enough entanglement might have an emergent geometric description involving black hole-like regions. Level 7. Cosmological black holes. At the final level, you realize that black holes aren't just objects within the universe, they might be universes themselves. And our universe might be the interior of a black hole. This isn't science fiction, it's the logical endpoint of taking black hole physics seriously. You encounter the idea that black hole formation might create new universe branches. When matter collapses to form a black hole, the interior spacetime might expand into a new cosmological region, a baby universe that grows from the black hole's interior. Our Big Bang might have been the formation of a black hole in some parent universe. At this level, you grapple with the idea that the arrow of time itself might emerge from black hole thermodynamics. The second law of thermodynamics, that entropy always increases, might be a consequence of the universe containing black holes whose entropy grows as they absorb matter and merge with each other. You learn about the cosmic census of black holes and realize that supermassive black holes seem to have formed impossibly early in cosmic history. The standard model of black hole growth can't explain how billion solar mass black holes existed when the universe was less than 1 billion years old. You understand that our observable universe might be bounded by horizons similar to black hole event horizons. All the information within our cosmic volume might be encoded on a two-dimensional boundary surface. Our three-dimensional universe might be a hologram projected from its cosmological boundary. At this ultimate level, you realize that the distinction between inside and outside a black hole breaks down entirely. In eternal inflation models, our observable universe might just be one bubble in an infinite multiverse, each bubble potentially the interior of a black hole in some higher dimensional space. The deepest realization at level 7 is that black holes force us to confront the limits of physical theory itself. They sit at the intersection of general relativity, quantum mechanics, thermodynamics, and information theory, and they're telling us that our current understanding is fundamentally incomplete. Black holes might be telling us that space and time are emergent phenomena, that information is the fundamental currency of reality, and that the nature of existence itself is far stranger than we ever imagined. They're not just the most extreme objects in the universe, they're portals to understanding reality at its deepest level. So the next time someone tells you they understand black holes, ask them which level they're operating at. Because the deeper you go, the more you realize that black holes aren't just astrophysical objects, they're the universe's way of teaching us that reality is far stranger and more wonderful than we ever dared to imagine. And maybe, just maybe, the boundary between observer and observed, between mind and matter, between inside and outside, might not exist at all. That's the true terror and beauty of black holes. They don't just challenge our understanding of physics, they challenge our understanding of what it means to exist in the first place.